All right, so here we're going to look at the second part of 12.3. Still focusing on determinants, we're going to start using the determinant to help us find inverses by hand. And as you remember, because we've done a couple of these so far, finding the determinants of stuff always has that subtraction sign in there, and then it's the diagonal starting in the top left. 3 times 3 is 9. Subtract 4 times 2 is 8. This one has a determinant of 1. All right, so remember to start off with that subtraction sign to catch your double negatives. Here we've got a negative 9. Subtract by the negative 6. Double negative there telling us this determinant is a negative 3. All right, so we see the word determine in the determinant because the determinant helps us decide if we're going to have an inverse or not. And the only thing that stops us from having an inverse is if your determinant is equal to 0, then matrix A that we see above there would have no inverse. No matter what you do, you'd never be able to find a matrix you could multiply it by that would cause it to create that identity matrix. Because as you recall, whenever we multiply a matrix by its inverse, assuming it's a 2 by 2, you always get this shape. All right, that's what inverses do. They cancel each other out to the identity matrix. But if your determinant is 0, you'd never be able to find one to make that happen. Okay, so if the determinant of A is not equal to 0, then it has an inverse written kind of seen above, whatever the name was. It doesn't always have to be A. Could be B. Could be H, matrix H. It'll have that little negative 1 exponent up top. All right, here's the formula. The inverse of A is going to look like this. 1 divided by always comes with the formula, always going to be there. Whatever your determinant is becomes the denominator. And then we've got a special little relationship with the various internal parts. A and D swap places. All right, and B and C switch signs. All right, and not with each other, but just overall. They're both going to change signs. So positive to negative, negative to positive. And this is the process that if we do this little formula, which you will want to memorize, but it's pretty easy. It's 1 over the determinant. Swap A and D. Toss some negatives in on B and C. Will help us find the inverse matrices. All right, so let's check this first guy out. The first thing we need to do is find the determinant to determine if we have an inverse or not. So I'd have 9 minus 4 times 2 is 8. This one has a determinant of 1, which is very convenient. Because now here in our formula, the one that we just found is the one in red. I need to swap my interior pieces. Now, the A and D are both 3. So when I swap these, nothing ends up happening anyways, which isn't the best problem writing on my part. But the next one they'll swap, so it'll be okay. And then the B value grabs a negative sign, and the C value grabs a negative sign. Oh, sorry. 2. Okay. All right, now normally we need to multiply this in and distribute it to all, but it's a 1 over 1, which is just a 1, so it's not going to change anything. So our final answer here, our inverse of A, would just be the 3, the negative 4, the negative 2, and the 3. So if you took this matrix and you multiplied it by that, they would become this identity matrix here. All right, so let's see one here where the determinant's not going to be 1 to kind of get that happening for us. So here we've got negative 9, subtract from the formula, a negative 6. Double negative here to get our determinant is a negative 3. So I set up the formula. The 1 divided by always comes with it. There in red is our determinant. And then back here in this original matrix now, I need to swap the various values. which is A and D swap places. So now that's a positive 3. Now that's a negative 3. Then B and C both gain a negative, so it goes to negative 6. Negative 1's already negative, so it turns positive. And now this time we're going to have to distribute in that scalar of negative 1/3 to all. Now if this freaks you out, think about this logically. All that's going on here is the 1 just tells you to keep your denominator the same, but then you need to divide it by a negative 3. So from a mathematical standpoint, all we're really doing is dividing all of those numbers on the inside by a negative 3, which would get us our inverse matrix being, well, 3 divided by negative 3 is a negative 1. Negative 6 divided by negative 3 is a positive 2. 1 divided by negative 3 is a negative 3. 1 divided by negative 3 is a negative 1/3. Because 1 divided by negative 3 would become a fraction. And then the negative 3 divided by negative 3 is a positive 1. So once again, if we multiplied this matrix A, or these two matrices together, they would cancel out to be that identity matrix. Alright, so we'll cover this last part. This is kind of interesting to see. We don't have to read back through all the information. But what it's talking about here is cryptology, which is kind of putting codes onto information. And this is what we still use to some extent today, especially when sending data across like online servers. And so you'll hear this in the word now, encrypted, when there's like encrypted data. And what that means is even if you get a hold of the data, you won't be able to read it because it's been scattered through some type of code. And this is what is kind of used to send credit card information across the internet without the fear of somebody grabbing onto the data stream and grabbing a hold of it. Because at this point, if you're encrypting things, you could stream all of these numbers across like the news, but nobody would be able to know what the actual data was. And here's kind of how it works. So if I take, and I'll just make a matrix here of these credit card numbers, and it can look various different ways. This is just the way I'm going to choose to set mine up. So say you swiped your credit card, it stored your credit card numbers here, and then they needed to send that information to the bank, but they don't want to just put your credit card number information out there. So what they could do is come up with just some random code matrix. Maybe they picked 5, 8, -1, 7. Who knows? Just 4 random numbers. And they just keep it random to where, you can't find any type of pattern on it, whatever. And then, if you toss that code matrix out in front of your credit card information, what it will do is it will just scramble all of those numbers up. So the result here would be a matrix that has still your information in it, but it's shrouded or hidden by the multiplication process of all those numbers. And if you think about what matrix multiplication does in terms of the rows and columns, there's going to be tons of numbers generated by this, and it would be impossible to kind of backtrack through this unless you knew the inverse of the code. So then what happens is whoever you're sending this information to would receive the code matrix kind of attached with your information. And then if they apply the anti-code, these will cancel out, leaving you back over with your credit card information. So that's the encrypted process of how you can send data across servers, and they can grab the data all they want. They're never going to be able to figure out what the initial matrix was unless they know that coded matrix's inverse.